In this video I want to show you what the D latch and the D flip-flop do have in common, what is the difference and how you can think of a D flop being built by using two D latches and a NOT gate. Recall that the D latch is this sequential element that you get here in the middle, the element that we used so far, and the D flip-flop you get next to it on the left-hand side. Now let's first see what they do have in common. If I set here the clock to 0 and change D from 0 to 1, nothing changes. You see that in the D latch a 0 is stored, and only if I turn the clock from 0 to 1 this new data gets copied into a D latch. Something like that you also can observe here. Now I also have here a D flip-flop with a 0 stored. I change the new data to 1, nothing happens. If I change the clock from 0 to 1, this new data gets copied into the D flip-flop. So this is what these two sequential elements do have in common. Now let's go back to the D latch. The clock is still at 1. I change D from 1 to 0, and because the clock is still at 1, the input port is still open and you immediately copy this new data into this D latch. This is something that you do not observe here. If you change here D from 1 to 0, the clock is still at 1, nothing happens in here. So this title, positive edge triggered, somehow indicates what is going on here, or how we could describe it. If you consider the clock as a signal that is time dependent, because at a certain point of time you either have the value 0 or 1, then you can consider the graph as a wave function. And when I turn the clock from 0 to 1, this wave function jumps from 0 to 1, so you have in the graph or in this wave a positive rising edge. And it seems as if this D flip-flop only in this instant of time, at this point of time where you go from 0 to 1, opens its input and lets the data being copied into the D flip-flop. Now this is just a mathematical description with simplifications. You know that in logic circuits, in the real world, you always have to deal with delays, and you never deal actually with a particular point of time. You always deal with small time spans where certain things happen. So I'm not talking about how you actually do realize that. That's something you have to ask the electrical engineers. I'm just describing what you observe mathematically. Now I also want to give you an idea how a D flip-flop can be built by using two D latches. And the reason for that is the mathematical simplified description of a D latch is very simple. You can use truth tables, or you can use a simple logical equation. That means if we have this understanding how a D flip-flop is built on top of D latches, we can, in a simplified mathematical model, describe how this D flip-flop behaves. And actually you already saw how a D flip-flop can be built with a D latch. You saw in these previous examples where we, for example, were building a counter, that we often used two D latches together and a NOT gate. And actually we discovered there are two variants that are helpful for this counter example. And basically you can think of this NOT gate doing the job of checking whether the clock was previously 0 and now is 1, or the opposite, whether it was previously 1 and now is 0. And in this variant you have a behavior that is the same as in the D flip-flop case. If you change the clock here to 0, change here D to 1, then this new data gets copied into this new D latch, and then you change the clock from 0 to 1, and then this data gets copied into the next D latch, like that. Now if you leave the clock at 1 and change D to 0, you do not see here a new data being copied into the D latch. It has no effect that you now change D. If you now change back the clock from 1 to 0, you do see an effect in the first D latch, but in the second you still have this old data. So this is the same that you discover here. I change D to 1, turn the clock to 1. Now if you think of this D flip-flop showing you this value, you see that if I now change 1 to 0, you still see the 1 in the second D latch. And that means in this configuration we have D flip-flop build that copies data into the D latch when we have a positive edge. Now in this variant we have the opposite. When the clock turns from 1 to 0, when we have a negative edge, the data will be actually visible here in the second D latch. Let's check this out. I change this here to 1. Nothing happens in the second D latch when I turn the clock from 0 to 1. But if I have this negative edge, when I turn the clock from 1 to 0, this new data is actually visible. That's what you also discover here. I change D to 1, turn the clock from 0 to 1. Nothing happens here. I turn the clock back, and now I see this. But now again, this here is a simplified mathematical description. Let's check out how this will no longer work if I, for example, change here the delay of this NOT gate from 10 to, let's say, 10,000. Now I set up a previous example. I turn the clock from the data from 0 to 1, turn the clock to 1, and then you see now immediately I also have the new data in here because this NOT gate was responding too slowly. And that means this simplified version is actually not doing the same thing as here, because as a mathematician I just thought I could use the circuit from above, like in the first variant like that, where I have here this NOT gate. Remove here this NOT gate and have it in here. Now this configuration would be the same as above, regarded as this configuration. If I change this configuration to this NOT gate, then I would have this, and then as a mathematician I thought, okay, here this NOT gate and this NOT gate, this cancels out. I just use here a plain wire, and I remove the NOT gate here. So I thought I would be smart, saving one NOT gate, make the hardware a bit cheaper. And this canceling out, as you saw, does not do the same thing if you have large delays in this NOT gate in here. So what I want to say with that is, if you want to know the technical details and how to actually build hardware that is working reliable, then you have to dig deeper. Then you actually should take some classes in the electrical engineering department. But for us, it simply means that we review our previous examples, for example, the counter example, where we, for example, had this configuration that we now would replace with a configuration where we use the D flip-flop with a negative edge-triggered behavior, or in this configuration where we would redo this logic circuit with a D flip-flop that is triggered by a positive edge. And of course, in this configuration, we also keep in mind that this is already some oversimplification in certain cases if timing is really critical. Then you also might want to look at this example with a so-called shift register, which also gives you an idea how D flip-flops work and how amazing it is that all these timings that are involved do actually work. Now you see here you have 4 D flip-flops. Let me zoom this a bit. And here I can change new data from 0 to 1, hit here this button, and then this new data gets copied into the first D flip-flop. But the remaining D flip-flops just get the value from the left. Now I change this here again from 1 to 0, hit the button again, and then you see that with this D flip-flops you're shifting data from left to right. And this, of course, if you consider what needs to be done in the real world in order to make this perfectly work, is amazing. Yeah? Because you have certain time constraints that the new data gets in at the same time the previous stored data gets copied to the next D flip-flop. This details about how to realize this, that all these timings are considered. That's a challenge on its own. That's why it's important to have experts that make these things happen that we simply just describe in a simplified way. Okay, so that's it for this video. You can see that on the website. I provide you a link to this project so that you can play around with what you saw.